Hi folks, this is the International Baccalaureate Standard Level Physics 2017 multi-choice question. It's worth 30 marks and there are 30 multi-choice, so I thought I'd go over it with you to help you out. One of the beauties about doing multi-choice questions is it does give you a breadth of questions, so you can get a little bit complacent with just long answers. So having multi-choice questions certainly tests the knowledge right across the spectrum of physics content knowledge. So worth giving these a go, worth practicing multi-choice questions, because it certainly not only helps you with your multi-choice questioning, but also with your long answers. So you really tests you out. So the first question here, number one, is really to do with energy, is to do with work, force times distance, and we know that force is mass times acceleration. And if you substitute this in, mass times acceleration and distance, and you look at the units of each of those quantities, you can see that it's kilograms, meters per second squared, and then meters again from that distance, and simplified out, kilograms, meters squared per second squared. So not an obvious answer here, because of course the electrical energy, the idea around the energy is what's needed. Second question is probably a bit more is easy. The only quantity here that is a scalar is the kinetic energy. All the rest, velocity, momentum, and acceleration, have a directional quality to them. So that's definitely C. For number three, this is to do with kinematics, this question, and it's a trick question really, because you've got to find the distance between on the fourth second. So of course you've got to work out the distance at the fourth second. So of course it's starts at 0 plus half times 10 times 4 squared, because it's under the fourth second, comes out with 80 meters. So that's the distance, total distance done in the fourth second. And you'd think, oh, well, that's 80 meters, but it's not. You've got to also work out the distance to the third second, which is 0 plus half times 10 times 3 squared. So that's 45 meters. So it's the difference between them. So it's 80, take away 45, gives you the 35 meters is the actual distance travelled in the fourth second. This particular graph here, what's happening here is this is a velocity time graph. So you've got acceleration here because the gradient isn't 0, and then of course it's constant. The gradient here is 0, so therefore there is very constant velocity going on here, because the gradient is 0. So in a distance time graph, this would be accelerating here and a constant here. So a constant velocity there, because of course it flattens out, and then of course decelerating back to 0. So this is the only graph that would mimic that. This is a trick question really. If there's constant speed, basically the net force is 0. So if there's no change in speed, therefore there's no acceleration, and therefore there can't be any resultant force. So the answer is A. Number 6 is really to do with net forces, and if you to draw a diagram of the forces on this elevator, this lift, you'd have the tension force on the rope, or the whatever it is, the chain holding the lift, the elevator, and this we know that the acceleration is 2 meters per second squared going down. We know the weight force of the lift is 7,500 newtons. Okay, and so this particular situation is not an equilibrium because it's accelerating. So the net force on it is 1,500 newtons. So basically it's 750, that's the mass of the lift, times 2, which is the 1500, and it's going down. So we know that the tension force is going to be the 7,500 newtons, take away the 1,500 newtons going down, and that will give you the 6,000 newtons in the tension force. Okay? Here, this is relatively easy question. Number 7 is basically the work done as the area under the graph, force times D, so the answer is C. Here, the power of the car is work divided by time, force times distance. 1,500 times 100 divided by 5 is 30,000 watts. So a reasonably straightforward question. Again, in number 9a, a relatively straightforward question. This is an inelastic collision. Okay, so we know that elastic collisions where both momentum and kinetic energy are conserved. So in this particular case, only momentum is conserved because it's inelastic. Here, number 10, a liquid is initially at its freezing point and energy is removed at a uniform rate from the liquid until it freezes completely. The answer is A, is because the temperature remains constant, remains the same. It's to do with its latent heat. So this is the heat being taken out of the liquid, but of course the temperature remains the same. Even though Q changes, the heat's been removed, it's just that the temperature remains the same. So again, slightly tricky question, but you have to understand about what's happening with latent heat energy. Number 11 is not really a physics question, it's more about algebra really, and it took me a little bit of time to sort of work this out. So we're really considering this area of the cylinder sitting on the flat surface. So that's what we've got to work out. We've got to work out the area of that very thin rim sitting on the flat surface, and that's what causes the pressure. So here we've got the definition of pressure as force divided by area, and that force of course is the weight force of the cylinder. But just one thing to notice is that they're saying that R is much greater than X. So it looks like X it's very thin, it's very, very small compared to the radius of the cylinder. But anyway, let's work this out. I think I just put in some variables here just to help me out, and I said that D is equal to R minus X, okay? R being the radius of the cylinder, and X being that little thin bit of area there on the rim. That's what we're wanting. We know that area is pi r squared, that's in a circle, and so therefore we have to pop this into the equation because that's what we're wanting to find out. We're wanting to find out the area of this thin piece that sits on the flat surface. So it's going to be pi r squared minus pi d squared because that's the area that we're wanting. And of course you've got to expand that out. We've got to find out what d squared is, and d squared is equal to r minus x in brackets squared. So we just expand that out and we can eliminate some of the variables here, and it comes down to the weight force divided by 2 pi rx, and I'm assuming that this small variable here, minus pi x squared, is so small that in fact we can ignore it, so that your best answer is A. Number 12, really to do with the ideal gas formula, PV equals nRT, and EK equals 3 over 2 kT, and if we rearrange that, we can see that as pressure is constant, and if we increase the volume of the gas, if we increase the temperature of the gas, if the temperature is doubled, we know that the volume will be doubled. P remains constant. Okay, so these are all things that we can look into the formula. We know that the N and the R, the number of moles, and the constant there is constant, and we know that pressure is constant. So these two variables here are proportional to one another. The temperature goes up, and so does the volume, and it will be 2V as your best answer. Number 13, again, relatively straightforward if you understand simple harmonic motion. And I suppose the best equation really to look at here is acceleration is equal to negative omega squared x. And you can see from the graph, and I always think of the best way I think of simple harmonic motion is using, just imagine a simple swinging pendulum. So here we've got maximum velocity, this thing swinging backwards and forwards, and at these particular points here, this is where maximum velocity is. And of course, at that maximum velocity is where a equals 0, because there's no change to the speed. The speed is at a maximum, so there's no changing speed, and so therefore the acceleration is 0. So your best graph here is number A, and it's because it's starting here at 0. The maximum must be at a 0. So that's your best answer there. Number 14, I suppose you've got to really understand the electromagnetic spectrum. And know that X-rays have a higher frequency than UV waves. So just the best thing to do with this type of question is know your electromagnetic spectrum really well, where the visible spectrum is, where infrared, microwaves and X-rays are, and where they sit on that spectrum, and your answer will be B. Number 15, again, quite simple. Basically, you've got two waves. It comes up, this type of question comes up a lot. And when they've got the same amplitude and they're on the same side, okay, then the waves will overlap and be on the same, be upside, and they'll overlap. So the answer is A, and it's called an antinode. Number 16, here you've got two polarized sheets, and one of the sheets has rotated at 90 degrees, so they're saying that it's perpendicular, and therefore no light comes through, or you get total polarization. So they're asking you now what happens, what angle will cause a quarter of the light, and the answer is 45 degrees of rotation. So half of the 90 degrees will cause that amount. And obviously it doesn't matter, it's all to do with comparison, so it can be either one of the sheets is rotated. So the answer is C. Number 17, hot air. Again, you have to understand about energy in hot air and cold air. Hot air to cold air, temperature drops, but there's less kinetic energy, less vibrations, sound travels slower, and if you use the wave equation V equals F times lambda, you get a drop in velocity, you'll get a drop in the wavelength, and F stays the same, okay? Just a note, the number of waves per second remains the same. So you've got the same number of hertz. It's just that as the wavelength decreases, gets smaller, so does the velocity, okay? Number 18 is really reading off the graph, and you can see that V equals IR, so that's going to be 6 volts, coming up from 6 volts and 9 milliamps, so it's just converting that, and you've got 666 ohms, which is your resistance. That's pretty straightforward. Number 19, the best thing to do here, and for all exams really, is to make sure that you know all your prefixes. So centi, milli, micro, nano, pico, tera, giga, mega, and kilo. So just know those, and knows those prefixes really well. So here we've got the kinetic energy is the volts times the charge on the electron, 2.5 times 10 to the power of 6 times 1.6 times 10 to the power of negative 19 coulombs, and out pops your answer. It's 0.4 times 10 to the negative 12 joules, which is 0.4 picojoules. So easy to make a mistake there, but actually relatively straightforward question. Number 20 is to do with EMF, electromotive force, and it's to do with the total energy of the circle. So you've got to add up the total energy of both from the battery and from the resistor. So we've got 1500 plus 2500, and you divide that by I times T, which is 4 amps times 500 seconds, and your answer pops out to be 2 volts. So just remember that EMF is the total energy of the circuit. Number 21 is really a trick question, because in a magnetic field, an alpha particle is a positively charged particle. It's basically the helium nucleus, and of course it won't have any force on it because it's in a magnetic field, and magnetic fields only interact with negative charges. So you just have to understand that, okay? If it was in an electric field, well, then that's different. An electric field can interact with both positive and negative charge. Number 22, you have to understand these two formulas here. Acceleration in circular motion is equal to v squared over r. And we know that velocity is distance divided by time, so that's 2 pi r over t. So if we wanting to make A the subject, it'll be 4 pi squared over r over t. So if for this, in this particular case, if v increases, so will r. If r increases, so if r is doubled, v is doubled, and so is A. A is doubled too. So it's a proportional thing in this equation. So as long as you know those equations, and you can do a lot with those equations, you can just about answer every question on circular motion. Number 23 is to do with a tension in a string or in a rope between a mass and someone turning it around in a circle, in a horizontal circle. So there's the tension there going from the mass to the hand of the person, pulling it round. So again, going back to the formula, F equals mv squared over r. Let's rearrange that. So we've got v squared is equal to F over m. Now, that from just reading the question, we can see that the breaking strain of that remains the same. So F divided by m is basically fixed in this formula, okay, in this particular situation. So we know that v squared is proportional to the radius. If we square root the radius, it's proportional to the velocity, okay? So if we double the radius, we get square root of 2, which is the speed required. If we go 4 times the radius, it will be 2 times the speed required, and so on. So the best answer here is A. (24). This is a classic nuclear reaction, and we're looking at positron decay, and a positron has a positive 1 charge, and that's the symbol there, and you've got a neutrino. So it's that's what you have to understand. Number 25, what is the definition of the unified atomic mass? Well, it's really straight from a textbook. It's A, 1/12 of the mass of the neutral atom of carbon-12. And the same thing with 26, it's number A. It's greater than 1 there. 27, what you have to understand is that 1 electron volt is equal to 1.6 times 10 to the negative 19 joules. And that the energy equivalent of a proton is 938 mega electron volts. And you're given this in this formula. So of course we need to multiply the 9.38 mega electron volts, which is 9.3 times 10 to the power of 8 joules, electron volts, times 1.6 times 10 to the negative 19, and that will make it into the joules, and that's your answer there, D. 28 is relatively easy. The only thing really standing out there is crude oil being the primary source, so they're wanting secondary energy sources, so it's going to be a battery and the pumped storage of hydroelectric system. So 1 and 3 only, number B. 29, this is about black bodies of planets, and here you've got a black body depends not only on not on the surface but its temperature, and you can see the best answer here is D. Number 30 is to do with power, and I had to look back on the notes here, so because I wasn't familiar with black bodies and planets, but it looks like the Mars to Earth ratio is 200 and has to the power of 4, and then divided by 300 to the power of 4 also. So you've got a 0.2 ratio between the power between Mars and Earth. We're talking about the power, the energy, okay, between the emitted, okay. But of course we mustn't forget that the radius of Mars is half of Earth. So therefore, if we're wanting to find the area, which of course is involving in this, and if you go back on the notes, you can see that the area will have a significant effect on the amount of radiation. We can see that that has to be half squared because of course pi r squared. And if you pop that in, and if you go 0.5 squared, Mars is 0.25 smaller in area because of the radius is half of Earth. So of course you've got to put those two factors together. 0.2 times 0.25 gives you the 0.05. So the answer is D. Thank you.